and we start out with normal distribution with 0, 1, which is a standard normal distribution, right? And we're going to derive the MGF of this first, and I'll show you how that connects to deriving the MGF of the generic standard distribution. And we start off, remember, we're going to remember that the MGF is what? It's going to be, so what, okay, and let's remember normal distribution has support defined everywhere in the real numbers, so we still have negative infinity to positive infinity. And I'm going to go ahead and add this term as well to part of it. So what's the probability density function? It's going to be e to the negative x minus mu squared over 2 sigma squared square root of 2 pi sigma and plus this term. But remember that mu is 0 and sigma is 1, so we can just kind of simplify this briefly with negative infinity, positive infinity, plus this term here. That's where it goes. And we're briefly going to check this out down here. In the exponent, we have x squared over 2. We're going to complete the square. Do this very fast. So complete the squared. How? By adding, well, you'll notice that if you take out negative 1/2 from here, you get x squared minus 2t x minus t squared plus t squared. Okay, now this you'll notice this part and this becomes what? It's going to become, excuse me, minus t squared, right? Because this resolves to x squared minus 2tx plus t squared. And so this is what we get. Now we distribute the negative 1/2, and what do we get? Plus t squared over 2. Okay, so this is our result. This is important. So look at this, because I'm just going to go ahead and put this into here. So let's do that very quickly. So this is what we have. And the reason is because I pulled out this, because this used to be, remember in here, what we just previously did used to be right there, but we pulled it out. I'm sorry that it does that. It's like some stupid software thing. I'm using a crappy little pad actually. So this is looking more and more like a Gaussian integral. And what is that? Gaussian integral is that Gauss showed that e to the negative x squared, negative infinity to positive infinity dx is what? It's the square root of pi, and particularly if this is a 0, it only is half the area, right? In some regard. It's a little more complicated than that because of infinity, but it's essentially that. There's limiting process. I'm not going to go into that, but in that case, it's pi is square root of pi over 2. Remember that. So that's important. Since we know that result, we just want to make this thing here look like this. Then we can resolve that integral. What we're going to do is we're going to say, well, look, we can just briefly use substitution here. So what do I have? Well, because u squared of this thing is going to be this, right? Which is exactly what we have here. So that's why I set u to this particularly. And then you have du equal to this. So we can go ahead and rearrange the integral. Then we have this. So this is what it resolves to from what we have. And you'll notice we can cross out the square root of 2's. They cancel out. And so we're just going to erase them. Done. And so what we have left is I'm going to pull out the square root of pi here. And we notice now that we can just resolve this integral because this is the Gaussian integral. Square root of pi times what? Square root of pi. Which means these cancel out and we have what? We have e squared of e to the negative t squared over 2, which is the MGF of the standard normal distribution. But now that we have this, let's just erase everything and move this guy up here. Okay, so the first theorem I want to bring up is the linear transformation of normally distributed variables. If you have y and w normally distributed, and this y is shifted by a and scaled, and w scaled by b, then the mean is the mean of w scaled by b plus a, and the standard, the variance is b squared times the variance of w, which, if you notice, let's say we have then generically, like, well, let's in fact let's say that w is exactly x, right? Then what is this then? This, well, the mean of x is 0, so this is just a, and the variance of x is 1, so this is just b squared. So if we set this to what? Just let's say that well, let's say that a, just briefly, is just generically mu, and that b squared is generically a variance, any variance. Then we have basically any normal distribution. So the second theorem I want to bring up is that you have two random variables and one is a linear transformation of the other, as we have here. Then the moment generating function of y is equal to e to the power of t times mu, this here, times the moment generating function of sigma t. Well, we know the moment generating function of this guy. So this does apply to us. Therefore, here we have e t mu multiplied by e to the negative t squared alpha, not alpha, sigma squared over 2, which is what? That's equal to, so that's equal to this, and this is the moment generating function of a generic normal distribution. So this is kind of a different way to derive an alternative way to derive the moment generating function for a normal distribution.